So whenever a wave hits a boundary in the medium, for example, it changes between two mediums, such as going from water to air, or say it hits a wall, then some or all of the wave is always reflected. And the amount of the wave that's reflected depends on the properties of that boundary between the two mediums. So for example, if we have this pulse traveling along the string and it hits the wall, it will be reflected as an inverted pulse because it will try to make the wall move by exerting an upward force on it, but of course the wall can't move, so it will just exert a downward force on the string, from Newton's third law, and this downward force makes the pulse be inverted and travel in the opposite direction. So this wall is an example of a fixed end, which is just an end that cannot move. So what happens when this reflected pulse and we have another pulse traveling in the opposite direction? What happens when they overlap? Well, when two waves overlap, we have what's called interference. And so we can find the total displacement at a point when multiple waves overlap by just adding the displacements due to each individual wave. And this is known as the principle of superposition. So let's say we have this wave here, which has an amplitude of 4 meters. And it's overlapping with this wave down here, which has an amplitude of 2 meters, but in the opposite direction, as you can see. So when they overlap, the total displacement will be 4 minus 2, or 2 meters. So instead of these two individual waves, we just see one wave with an amplitude that is the sum of the amplitudes of the original waves. So when we have a string with a fixed end, the waves coming from the source, like here, and the waves reflected off that fixed end can interfere to produce what's called a standing wave. So a standing wave does not look like it's moving anywhere. It just kind of vibrates in place. So you can see all the particles here are vibrating together. They all move down and then up, and then down and then up. And so as we make this string longer, we get more of these little sections where the string is vibrating in phase down and up, down and up. And you can also see that there are some points where the string is not moving at all. And there are other points where the string is moving the most. Like say here, the string is moving up and down with a greater amplitude than these other points here. And so these points where the string is not moving are called nodes. So at a node on a standing wave, the displacement is always 0. And that's because the two waves that make up the standing wave have what's called destructive interference. And that's when the two waves, they cancel each other out. Say this wave has a displacement of 4 meters in this direction, and this wave has a displacement of 4 meters in the other direction. So by the principle of superposition, if we add their displacements when they overlap, it'll be equal to 0. So we don't see any displacement at all. And remember, that's destructive interference. And these points where the displacement reaches a maximum are called antinodes. And at the antinodes, the two waves add up to produce an even larger displacement, which is called constructive interference. So, that would be like if the two waves, they both had a displacement of 4 meters, but pointing in the same direction. So when you add them, the total displacement would be 8 meters in that direction. So they add to produce an even larger displacement, than either of the two individual waves. So we can find a function for the standing wave. So this equation gives the displacement from equilibrium of any point along the standing wave. And the amplitude of a standing wave will be twice the amplitude of the individual waves. And that's because the amplitude is at the antinodes where we have that constructive interference. Remember, the two waves add their amplitudes together. So in terms of energy in a standing wave does not transfer energy from one end to the other, like in a normal traveling wave. Because you can see, this wave is carrying energy in this direction, and this other wave is carrying energy in the opposite direction. So in total, the average power of the standing wave is 0. So now let's look at what happens when you have a string that is fixed at not one end, but two ends. So of course at a fixed end, the string cannot move, which means the ends of the string must be a node. Remember, at nodes there is no displacement. So since nodes are half of a wavelength apart, then the string's length must be an integer multiple of 1/2 of the wavelength. If it's not an integer multiple of 1/2 of the wavelength, then both of the ends cannot be nodes, which would mean, one of the ends would have to be undergoing displacement, which is not possible if it's a fixed end. So these are all the possible lengths of the string in order for the standing wave to be present. Now, rearranging this equation and substituting with frequency, we can find all the possible frequencies that the standing wave can have. So on a string with a length L, where the wave moves through the string at a speed v, then to get all the possible frequencies of the standing wave, we just take this and multiply it by any integer, which is that n. So the lowest possible frequency when n is equal to 1 is called the fundamental frequency. And all the other frequencies are just integer multiples of the fundamental frequency. And those other frequencies are called harmonics or overtones. So if you play a stringed instrument, you can see how this equation applies in real life. So when you put your fingers down on the string, say you're playing a violin, then that effectively decreases the length of the string. So when you put your fingers really up on the fingerboard, then the string will be shorter, and the frequency will therefore be higher. Which is why when you play the notes where your fingers are really up on the fingerboard, those are the higher notes, because the length of the string is shorter and the frequency is higher. Now the wave speed, remember, in a string depends on the tension and the linear density. So when the tension in the string is higher, the speed is faster and the frequency is higher. So on a violin, for example, the E string is stretched the tightest, the tension is the highest, and therefore the wave will travel faster through it, and the frequency is higher. So the E string is the highest sounding string, because the tension is higher than the other ones. Now the G string is the thickest string. It has the highest linear density. So the waves will travel slower through it, and the frequency will also be lower. Which is why the thicker strings sound lower. They have lower notes than the other strings. So each oscillating system has normal modes, and a normal mode of an oscillating system is a pattern of motion in which all the particles in the system are oscillating with the same frequency. So each of those harmonic frequencies given by the equation above correspond to a possible normal mode. So a standing wave on a string has basically an infinite number of normal modes. You can make that n in that equation whatever you want. So there are infinitely many harmonic frequencies on a string. Whereas before, when we had just had one particle undergoing simple harmonic motion, such as a simple spring system or a simple pendulum, there is only one normal mode, because there's only one frequency that the system can oscillate at. And remember that frequency, that one frequency that's possible, is given by this equation, 1 over 2 pi times the square root of k over m. So that's the only frequency that that system can oscillate at, and therefore there's only one normal mode in a simple oscillator. So all this time we've only been looking at the sinusoidal waves, which remember is when all the particles are undergoing simple harmonic motion. However, of course, in real life, the actual waves, such as on a stringed instrument, are much more complicated. So it contains, when we pluck a string on a stringed instrument, the frequency there will be multiple frequencies. There will be some of the fundamental frequency, which is what we hear. We perceive as the pitch of the sound is the fundamental frequency. But there are also many other harmonic frequencies as well. And so it turns out these sinusoidal waves are so useful because we can represent any complicated wave as a superposition of many normal mode motions or sinusoidal waves.